with lecture on gambling, so be prepared to have £5 ready. So, we have David Aldous of the Compulsive Gambler.
Okay, thank you very much. It's always a great pleasure to come back to Cambridge. I've spent the 70s in Cambridge, and it's changed somewhat, but fun to be back. Okay, let's get organized. Okay, what am I pointing at? Forwards, backwards. Okay, so there's a sort of bit of a background program here. I'm not used to looking at what I'm saying, so let me try and remember what I'm looking at here. So the class of models which we call interacting particle systems, and it derives very clearly from Liggett's book of that name. You know, math gets trapped a bit by its history. These came from physics, and if you think of the stereotypical model of this type being the sort of three-dimensional Ising model, you think in terms of the structured space of sites. You think in terms of categorical variables, spins plus or minus one. You think in terms of phase transitions for infinite systems. On the other hand, sort of partly independently and partly sort of as a development of this, there's been sort of a lot of use of similar models like the voter models in many other contexts. In particular, I think of sort of social networks of people interacting. And so even though you can use things like the voter model in both contexts, there's a slightly different sort of conceptual background for social networks. You have sort of unstructured networks. We don't live on a two-dimensional lattice, even though people occasionally pretend we do for mathematical purposes. Often we think of numerical states rather than categorical states. And somehow we're in these sort of finite systems, so even though people like to talk about tipping points as a sort of social analog of phase transitions, we're also sort of concentrating a bit more on finite time behavior, as in sort of Markov chain mixing times. So we think of slightly different things. So I have a little formalization of this. I mean, there was never any very precise definition of what an interacting particle system was, but one can do a slightly more precise definition of a kind of strongly overlapping context, and I just make up this rather ugly name, FMIE, for sort of finite Markov interchange processes. So I think of a sort of finite number of agents, people, each having some state, maybe discrete or continuous. Each pair of people meets at some rate, meets at the time of a pass-on process of some rate, and when two people meet, they update their states. You come into a meeting with some pair of states, you go out with some pair of states that may be deterministic or random. So somehow the voter model and most of the named models we're familiar with simply correspond to some update rule, deterministic or random. But kind of the part of the focus is to sort of think of our underlying structure, which is kind of a finite weighted graph. We identify the edge weights with meeting rates across edges, and somehow instead of concentrating on sort of sharp computations for a particular sort of geometry of this meeting rate process, we like to think more generally, kind of weak results for general meeting processes. Rather than thinking sort of exactly what happens on the three-dimensional lattice, for example. So I'm going to briefly talk about maybe the simplest model of this type, and then jump on to the particular compulsive gambler problem. This is joint work with my student Dan Lanouille in the back, second row from the back, who, as usual, will answer any technical questions here. So there's a simple version. It's something called, I call an averaging process. It's been sort of studied in sort of CS gossip algorithms. Here, what I'm saying is all fairly straightforward. So here, in both examples, an agent state is their amount of money. The averaging process, whenever two people meet, they share their money equally. So what could be simpler than that? And of course, a number of things are obvious. Eventually, of course, everyone's money is going to converge to the average. Again, we're on a finite system here, so things just average out. What's interesting about this is there's a relationship between this process and what I'm calling the associated continuous time Markov chain on the state of agents, that is the continuous time chain where the transition rates are just the edge weights. This always has a uniform stationary distribution, it's worth saying, just by sort of symmetry here. And the relationship is sort of written out in the lemma if I think of starting the averaging process where one person has 1 unit money and everything else has 0, then the expectations in the averaging process of how much money people have different individuals have at time t evolves exactly as the transition probabilities, the PIJTs in the continuous time Markov chain up to a time scaling of about a half. And basically, the way you can do that is you kind of think of atoms of money, and the process of 2 people sharing their money equally is the same as the process where sort of for each atom of money, a person tosses a coin to decide whether to give it to the other person or not. So you're sort of following this sort of typical atom of this system evolves as the Markov chain at half speed. And this, by linearity, this is saying that the derivatives of the expectations in the averaging process are behaving as this little differential equation that associated with the generator of the Markov chain, that the same equation that determines transition probabilities as a function of t. What am I doing? Sorry, I'm getting confused at my labelings, at my things here. Okay. So in terms of sort of global rates of convergence to the limit average, we can scale everything so the average monies is 0. So the time t configuration of money is converging to 0 as time goes to infinity. How fast does it go? So we sort of measure sort of global deviations from uniformity as the L2 metric. Again, this is L2 over agents, not L2 in the probability sense. And then you look at the expectation of this sort of L2 measure of global variability. Again, it starts off as the initial L2 variability, and then it goes down exponentially at a rate connected to the spectral gap of the associated Markov chain, which of course controls the rate of convergence to the Markov chain. So not only is sort of kind of as applied by the previous lemma, not only is the rate of convergence of expectations connected to the associated Markov chain, of course ultimately depends on the geometry of the meeting process, but also this the sort of stochastic version, the sort of global measurement of non-uniformity. And a slightly more intriguing idea, it's one of those ideas where there's some intuitive idea that a priori you think might be very hard to formalize and turns out to be easy. I got to add a bit more assumption, normalized meeting rates for each person, the total rate at which they meet others is 1. There's a little uniformity there. Again, we think of kind of the meeting rates intuitively as as a geometry. The people you meet relatively frequently are the people who are relatively close to you in some unspecified sense. So we're interacting with local people. Just jargon here, again for a function, g from the set of agents. We have our L2 norm as the variability. A standard idea is the Dirichlet form G, which is measuring local variability. So it's the L2 norm is a measure of the difference between two random agents, whereas the Dirichlet form is a measure of the distance between two nearby agents, weighted by how often they interact here. So the rate of convergence of sort of global variability depends a lot on the geometry of the meeting process. This is sort of the topic of mixing times to Markov chains. It turns out that in our averaging process, because you interact with neighbors, the idea that regardless of how fast or slow you converge globally, if you're interacting with your neighbors, the configuration of money should become locally uniform rather more quickly. And it turns out that if you measure the local uniformity by the Dirichlet form, then somehow we get this rather absolute bound that doesn't depend on the geometry, the integral out to time infinity of this sort of expected Dirichlet form variation just depends on the initial state, and it doesn't depend on the geometry at all. Now, this looks like magic, and of course we're cheating somehow, because of course the Dirichlet form itself depends on geometry, so it isn't quite as universal as it looks, but it does give a sense in that there's some behavior that doesn't depend on the details of the geometry. So let me sort of move on to what we're studying. This is a made-up process. It was made up humorously, many a truth hidden in a joke, because where does it come from? So if you say the averaging process, you maybe think socialism. So if the averaging process reminds you of socialism, what should remind you of capitalism? So, well, you may think of something else, but what came to me is, well, two people meet, and one of them takes all the money. There you go. But in a fair way. So I have 3 units, you have 5 units, we meet, then one of us gets the 8 units, but I have chance 3 and 8, you have chance 5 and 8. So whenever people meet, people get all the money. And of course, one way of thinking of this is sort of a coalescent style. So I'm going to draw pictures with the time going upwards. So I draw time going upwards. Everyone starts off with the unit money. The first 2 people to meet are these 2, and maybe if this person wins, this person gets 2 units of money, and then these 2 people meet, and if this person, so this person now has 2 units, this has 1 unit, so this guy has 2/3 of a chance of getting the 3 units, etc. But then maybe this guy is lucky and actually wins the 4 units, etc. So when we look at this in time, we have a tree. So there's some connection with the topic of this workshop. We have a tree, obviously a coalescent type tree associated with the process. It's a made-up model. It's interesting as pedagogy in the sense that there are a bunch of different techniques which are useful for studying the process, as well as intriguing analogies with other topics. So I sort of, for most of the lecture, I'm just sort of saying these techniques rather than theorems, and then I'll go on towards the end at sort of directions we've been thinking of using the techniques. I suspect there's quite a lot more to do, which we haven't gotten around to doing yet. So, again, the process is parameterized. There's a sort of finite n-vertex edge-weighted graph, implicitly connected. It's boring if it's not connected. But other than that, I think of the meeting rates across the edges as being arbitrary. So the first observation is supposed to run a complete graph, meaning all the edges have non-zero weight. Any pair of people have some chance of meeting. So it's now obvious that eventually somebody gets all the money. Everyone starts off with 1 unit. There are n units in total. Eventually some people get it just because the number of agents who have non-zero money. The word solvent here, sorry, non-English speakers. Solvent means you're not bankrupt. It means you have some money still. That number of people can only go down, and if everyone meets everyone, it eventually has to be 0. If we're not on a complete graph, then we might end up with 2 or more people who have money, but none of whom are neighbors in the graph. And then you're stuck, then the process stops. In general, the process will stop when we get to some set, which is an independent set in the graph. Of course, the terminology of independent set from graph theory is awkward, and anti-clique works better, a set of agents where no 2 agents are neighbors of each other in the graph. So if you think about the complete graph, but with non-uniform rates, a natural thing to do is to compare it with the complete graph with uniform rates 1, and this is essentially the Kingman coalescent, up to some details of exactly how much structure you think the Kingman coalescent itself should be. There are quite a number of different ways of sort of saying what the Kingman coalescent process is with more or less extra structure, but the number of lineages in the Kingman coalescent is exactly the same process as the number of solvent agents in this particular process, since this number of solvent agents, number of lineages is just a pure death process, there's an elementary formula for expectations of the coalescence time, and one can sort of trivially therefore get upper bounds on a kind of monopoly time t, the time until one agent has all the money in our process, in terms of the corresponding thing for the Kingman coalescent multiplied by either the maximum of all the edge weights or the minimum of all the edge weights. So that gives us a start here. Second idea, I said fair game. The word fair game, well, translates to martingale. So by definition of the process, if you follow one agent, all that happens is he occasionally plays a fair game, so the amount of money for one agent has to be a martingale. And now there are sort of more things going on. If I sort of look at the product of the numbers of products of the fortunes of I and j, xi, xj, then when there's a meeting which only one of them is involved with, because that person makes a martingale step, the product is a martingale. If they both meet, then one of them becomes 0. So this just tells you that the product has to be a super martingale, for example. Again, a linear combination of martingales is a martingale. So when we look at the sort of general linear functional of the vector of monies, that's a martingale. And again, you can bound in various ways. There are sort of other bounds which we technically use, but we can sort of bound the a second moment that we bound the variance of this in various ways in terms of the meeting rates here. So again, this is a natural tool. Just to say one more elaborate thing, and this kind of is an assertion that's sort of completely trivial to check. It took us a long time to think of it. So maybe there are actually more useful martingale things we haven't thought of. So if I somehow think of a general sort of quadratic form on the space of configurations, so I'm sort of fixing my symmetric function psi, 0 on the diagonal. I look at my capital psi of configuration of money x as the sort of quadratic form in x here, and then the psi sub nu is the sort of quadratic form but where I'm weighting the terms by the edge rates. Then just straight out of the definition of the process is when I look at the sort of expectation of the increments of the expectation of the psi, I get the psi sub v, psi sub new process. So I get this sort of martingale of the form stated, and again, this really just comes off the definition of the process. And now something magical happens that I sort of understand at the computational level, but it's not so intuitive what's going on. Again, in the complete graph setting, again, all the rates are non-zero, but they're otherwise arbitrary. Then if I apply this with psi as 1 over the rates, and then think of doing the natural thing of just applying the optional sampling theorem to this martingale and monopoly time t, then what comes out after a line of algebra and a simple application of Cauchy-Schwarz at some point is that the kind of naive lower bound on the time we get from Kingman coalescent sort of can be improved to this middle term, and essentially we're replacing the maximum rate nu star on the left by the harmonic mean of all these rates as the middle term. And again, this is something which kind of comes out of a computation, and in some sense this is the first non-obvious fact about this process here. The third methodology is the most interesting one, and at this point I need volunteers with £5 notes. Just come up here and nobody trusts me. I don't know what I have a bad reputation here. Oh yeah, somehow but yeah, you need the actual £5 notes here. Well, any number will do. No, I need you two. It works well. So just stay here for a moment here. So what we're going to say is that yes. The more the merrier. It's more exciting here. So I'm going to kind of do this process without randomness. So we're going to do a sort of... So what I say is we're going to meet, I meet you first, and instead of sort of doing what I said, instead of flipping a coin to decide who wins, we're going to look at the serial number and declare that the smallest serial number wins. So mine starts 1-3.
7-3.
7-3. Oh, good. Life is good here. Okay, thank you. And now we do the same thing. We will let the two of you play. You two meet. You read the first digits of your serial number.
Would that be 2-4?
Yeah, 2-4.
I have
8-5.
8-5.
The lowest wins, actually. It's arbitrary convention here. And then we go on like that. Then next we meet, and now it's we compare our lowest numbers. 1-3. Well, yeah, well, thank you. See this? I like this. You see why I like this game. Okay. Okay, there we are. Well, thank you. Okay, so thank you for the assistance here. It's if I offer to saw somebody in half, don't volunteer for that one. Yeah. So it's okay. So there's this. Another process. So another process is where we sort of have the meetings go on as before. And in this particular process, only the first meeting of two people is ever going to matter. So the underlying structure is this weighted graph, but a single exponential random variable on each edge for the first meeting time of the two people. But again, these with sort of arbitrary rates here. So people meet in this way. But now the idea is, well, I give somebody what we later call a token, but I think of as a banknote with a random serial number on it, and then the winner, instead of being determined randomly on the fly, the winner is always the possessor of the lowest numbered banknote. So the sort of winners are now sort of deterministic, but of course these are given out randomly in the first place. So it's kind of like dealing cards. When I calculate the probability of 5 cards being a poker hand, we kind of think of calculating that in terms of conditional probabilities, but of course it's determined by the initial shuffle, so we are sort of imagining all the randomness is done in the initial shuffle, and then we do things deterministically here. And again, there's a proof by careful induction, which I won't give. So this gives us the token process, and again, it's kind of writing out what happens in symbols is somehow harder than just sort of intuitively thinking about how the token process goes. So I'm now doing this with n people, sort of everyone in the room has a banknote, and we're sort of meeting arbitrarily. But the point being that, of course, the person with the lowest numbered banknote sort of always wins the bet. So the lowest numbered banknote stays with that person forever. Again, the person originally dealt for the second lowest banknote can only lose it to the lowest banknote person, so they keep that banknote, again ignoring what others they may have, they keep that particular banknote until they meet the first person and give it to them. And of course now it gets more complicated. The person with the third lowest banknote, they can only lose it to person 1 or 2, person with the lowest or the second lowest banknote. If the first of those they meet is the person with the second lowest banknote, then the issue is sort of whether that person has already lost the banknote to 1 or not. If they still have the banknote 2, you give it to them. If not, you win that bet because they have no money left, and you wait until you meet the person with banknote 1. But we just have this sort of deterministic but sort of increasingly complicated process for where all the banknotes go, and I can kind of construct the process. So instead of sort of constructing the process in time for everybody, I'm sort of constructing the process for all time, sort of note by note in this particular way. And this is very reminiscent of, if you know what the Donnelly-Kurtz look-down construction in population genetics is, it's a very similar idea. We've never been quite sure if there's a precise connection between the two, but it's familiar. And again, we have other analogies like this. And now there's another related idea. So we imagine. So we imagine we're sort of watching the process evolving, and so without loss of generality, we can assume it's evolving as this token process. you're seeing who beats and who wins the bet, but of course you're not seeing any of the banknote numbers. So at some point we started off with these 10 people, and at some point there's our configuration of money is these piles of 2, 4, 3, and 1. And I claim that sort of conditional on what you see there, we have the distribution of the banknotes of the ordered serial numbers 1 to 10 is some random distribution, but in fact it's uniform on all the possible ways. On all the possible ways we could sort of divide those 10 notes into a group of 2 and a group of 4, etc. And again, this is sort of not quite obvious exchangeability property, and again it's reminiscent of sort of similar ideas in exchangeable coalescent theory, and again we've never been quite sure exactly what the connection is. I mean, it's odd because sort of exchangeability, you're in Diffidetti type context, x1, x2, x3 being exchangeable, we think of kind of agents. So x1 is associated with person 1, x2 is associated with person 2, x3 is associated with person 3, so it's exchangeability over people. Here we don't have any exchangeability over people at all. This is because the meeting rates are entirely arbitrary here, but somehow it's this exchangeability over banknotes rather than over people. So it's a little sort of subtle to keep track of this. But this is a symmetry, so we have this partial, this sort of symmetry property at the level of individual notes. I'm going to wave my hands through some things for which the details are totally important, but there's sort of one feature which will come back later. So for several reasons, again, if we're in the complete graph setting where one person eventually gets all the money, then because they're playing fair games, everybody has the same chance of being the person who ends up with all the money, and the identity of that person is uniform over n agents. In terms of sort of computing things, if we look at this sort of arbitrary linear functional over agents, that goes as a martingale, but we can try and actually calculate moments of this, and I'll show a picture at the end, but in principle we have some formula for the sort of general case moment here. This formula involves a lot of things, so maybe I'll sort of indicate what we have to do on the, we'll come back to what the formula is and say how we go about it. So in order to like to think big here, so if I want to, instead of thinking about the 4th moment, I'm going to think about the 10th moment, just to get the complexity down. So I want to think about the computing the sort of 10th moment of this linear functional, again for some large number of people. This of course just depends on the distribution of k-tuples of notes, but the point is our sort of exchangeability property reduces the probability for a general k-tuple by exchangeability reduces to having to do a calculation just for the k lowest ranked notes, and this is easier to understand via the token process. So we have to sort of go through what the possible combinations of where those 10 notes may be in clusters. So a sort of typical one of many possibilities is a particular agent A has banknotes 1 through 4, B has banknotes 5 through 8, etc. And now we just start seeing how that could happen. Okay. Conference on trees. I'm drawing a little tree here. So somehow, in order for A to land up with, let's go with my. Somehow I have a dot I cannot see. Maybe I'm upside down. I think that works. Okay, I am totally incompetent with these devices. Okay, which way is this pointing? Where's the pointer? There's my pointer there. Okay, we are going to try once more. The other way. Okay. Okay. I think some odd consequence of being colorblind. I think I don't see this as well as you do. Anyway, yeah, so in order for person A to end up with 1, 2, 3, and 4, sort of some unspecified other people, A2, A3, A4, have to start it off with those banknotes 2, 3, and 4. and somehow they have to, whether or not they meet other people, sort of doesn't affect whether they are going to end up with person one at a given time. So we're only interested in the meetings amongst themselves, and they have to somehow have all met and joined up with the person who started off with 1 by a terminal time t. And then we want, try this here. Okay, so I am having great problems with these things. Where am I going? Sorry, I'm having problems with forwards and backwards here. So let's try and, because if I had numbers on here, that would help too. Dun, 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 dun. Okay, I'm going the right way here. Thank you. Okay, I'll try not to hit any buttons here. Yes. Oh dear. Okay, let's go back to yeah, right. So we wanted. Okay, not. Okay. All right. I'm going to point. Well, we need a large stick pointer. We have a large stick pointer. Ooh, life is good. Okay. Okay. Yes, we have 2 mathematicians who are Professor Greys. Have you ever thought of that? Two probabilists. Called Professor Grey. Okay, I'm sorry. Nobody's watched the movie here. Okay. all right. So we want person B to end up with 5, 6, 7, and 8. And now the point is for that to happen, sort of, again, somebody else has to have 6, 7, and 8, and they have to sort of meet up with each other at some point. But also, of course, they explicitly have to not meet with any of these people before they've sort of given away their money. So if this person was sort of meeting 3 here, then they lose their money to 3, and their sort of money would be ending up with this guy, not this guy. So we have sort of certain things have to happen, and certain sort of unwritten things have to not happen. So this is in some sense insanely complicated as sort of explicit formula, but somehow there are only a number of limited things that we have to count. We're sort of counting various combinatorial possibilities and integrating over time, and ultimately it's a sort of finite number of terms, which depends on the moment we're calculating, but in a certain sense doesn't depend on the n, doesn't depend on the number of agents we're looking at. Okay, so these are tools, and let me sort of go on to more what we can do with the tools. So again, there are quite a number of directions we can think of as doing. One, because it's another interest of mine, is kind of the sort of sparse graph limit setting. So here we're sort of maybe going to the opposite extreme from complete graphs. I'm thinking of a n vertex, R regular connected graph. I'm sort of fixing the degree R. We have uniform meeting rates over edges. I think of them as 1 over R, but it doesn't matter if they were 1. So again, the process now runs to a terminal state. Everyone starts off with a dollar, but we end up now with some random independent set, and so there's some eventual mean density, 1 over n times the mean number of solvent agents, and that's just some number that depends on the graph. Trying to compute this for particular graphs or trying to compute it exactly seems pretty tough. We haven't really tried that, but we're thinking of asymptotics as n goes to infinity. So the issue is I take a sequence of graphs, increasing numbers of vertices, but I fix the degree r, then there's some range of possible values for the limit of this a of g, and one question we ask ourselves is what's the range of possible limit values as a function of r? And this we can partly do. So we have bounds for finite r. Again, they're a bit messy, and I'm just going to state what these bounds are as r goes to infinity. So it turns out to be fairly easy to show that the sort of smallest that this quantity a of g can be as n goes to infinity, but for large r, is around 1 over r. The simplest, there's an obvious lower bound that for any g, we have A over G is bigger than 1 over 1 plus R, simply because in the token process, you get a banknote, your R neighbors get a banknote. If yours is the smallest of those R plus 1, then you can never lose a bet. You only interact with your neighbors. So that gives you a lower bound here. And now you can kind of construct graphs. So almost the first thing you think of is somehow to have a complete graph on a little, sorry, what are you doing it? Right, we start off with a clique. Okay, right. So I start off with a complete graph on R plus 1 vertices. Sorry, I'm getting confused here. So everything has degree R. I do the same thing over here, and I then sort of break one edge in here in order to connect it. And this is some sort of standard sort of extremal construction, and you can see that sort of so I take a whole bunch of those in a cycle, say, and it's easy enough to show that we get an upper bound of what AG is for this type of thing. So we know that the upper bound is more mysterious. We can do constructions where the limit A star R is sort of essentially computable and is asymptotic to 2 over R. These are based on looking at graphs that are locally tree-like and therefore whose local limit is the R regular infinite tree, and doing the analysis on the infinite tree. We conjecture this is somehow the worst case. There are many contexts in which trees are extremal, and it's sort of reasonable to guess this is one example, but we don't know how to prove that. So again, this sort of segues into another issue that a kind of nice feature of the compulsive gambler process, which we initially think of as again a process on n agents, is that one can think of sort of both types of n to infinity limit. One can think of infinite discrete space of agents, just like the infinite d-dimensional lattice or the infinite regular tree here, as one limit, but later on we can also think of scaling limits. We can think of a sort of n by n torus just going to the continuous torus and think about a continuous analog, and that will be our final topic. Analyzing these things on the d-dimensional lattice with nearest neighbors interactions, you can imagine by analogy with other interacting particle processes, and calculation is going to be very difficult to do anything explicitly, so we've been too scared to even try to do anything with that example. Doing it on the R regular infinite tree with just sort of constant rate meetings across edges, it's natural to guess you can do processes on trees by some sorts of recursion, and this works out here. Again, it's not entirely trivial, but it's not entirely difficult. I should say this part of the work was from Justin Sales. Again, so basically you can set up a recursion that gives you equations for the generating function, in variable z of the distribution of the amount of money at time t that a typical agent has. We can't sort of solve those generating function equations explicitly, but we can get bounds on the solution, and that's enough to, and we can get the upper and lower bounds well enough to estimate the proportion of solvent agents in the t to infinity limit, and for this tree we know it does go to 2 over r as r goes to infinity. There's a cuter side in the realm of connections with other things. I mean, we mentioned the Kingman coalescent as a simpler object for comparison. These recursive arguments, which we do on the regular tree, also work on Galton-Watson trees, and again, you sort of, for a general Galton-Watson tree, you have the equations, but you can't solve them, and we're sort of not smart enough to get information out of them without solving them. Where the sort of Poisson, the Galton-Watson tree with a Poisson mean is one of these natural objects, and in that case we can solve them, and again, we as in Justin, did solve them, and in fact you get this explicit distributions for what a typical agent has. Now of course this is an agent sort of unconditional on the shape of the tree. So if you don't know what the shape of the tree rooted at that agent is, that this is what we see. And basically conditional on being non-zero, we see geometric distribution here. And when I saw this, I said, okay, there has to be a reason for this, partly because I've seen this before. And the answer is it's the same as the sort of short time limit of the standard Kingman coalescent. So if you think of the Kingman coalescent in its sort of original story as the limit of Wright-Fisher lines of descent, you have sort of n genes in the current generation and working backwards. And if we think of, now we want to think of each pair of lineages as sort of merging at rate 1 over n, so the sort of time back to last common ancestor is order n here. So before we've rescaled time to get the standard Kingman coalescent. So that, again, the standard Kingman coalescent is telling us what happens to these lines over time order n, but you can also look at time order 1. Your initial line of descent is merging with somebody at rate 1, and the sort of short time limit, the time t generations back limit in Wright-Fisher of the kind of cluster size, the sort of number of lineages that have merged. And I guess we're now looking at unconditionally, the unsized biased version is exactly this limit geometric distribution, sort of short-term merging of lineages. And then you can see, and I haven't managed to sort of draw a good picture to explain this, but you can see that these two processes are really involved in the same way. It's slightly subtle to explain that, but you can convince yourself that it's not just a coincidence. These really are the same two processes. Okay. Another case which has sort of interested me in different contexts, again, looking at the regular lattice with nearest neighbor interactions is kind of hard. We can look at sort of allowing long-range interactions where the rate at which you interact with someone else is just a power, a sort of a negative power of the distance between them. Somehow this is sort of, this seems to be sort of a natural model, or the natural toy model for social interaction that takes into account space little, and for many years I've gone around muttering, why don't the interacting particle systems people actually think about these rates? And in fact, recently they have. I'm getting ahead of myself in what I'm saying. At the bottom here, there's a recent work by, this is Shendu Chatterjee and Partha Day, who've sort of studied within this framework. They studied, again, a different question, just the sort of first passage percolation associated with these percolation rates here. And again, that turns out to have a very interesting structure, in that you have sort of 4 qualitatively different types of behavior depending on what the parameter is. So I think there's lots of scope for studying different forms of interaction over this particular sort of long-range meetings on the lattice. And of course, what's happened is that people have looked at something superficially similar but different. People have talked about long-range percolation in the sense of the random graph gotten by choosing edges with this probability, but sort of it's one of those, I don't know, simulated versus annealed things. Sort of choosing a random graph and studying a process on a random graph is different from what we're doing here, where somehow there isn't a graph structure. We're just having meeting rates and these Poisson meetings going on forever, but you just meet close people more often than distant people. Anyway, getting back to my case here for the compulsive gambler here, intuitively it's fairly clear what happens, that the sort of the density of solvent agents should just be going down as a particular polynomial in time, the sort of mean fortune of a non-bankrupt agent obviously has to go down. It's exactly 1 over this density, but then the idea is when you scale back, when you look at the fortune at time t of somebody who has money and scales so that has mean 0, intuitively that has to be going to some limit distribution here. So the people who have money have more money, but they get more sparsely separated, and now it seems intuitively clear that if there should be some scaling limit if you just scale space to make the spatial density of solvent people stay 1, and sort of do our scaling of the amount of money such that their mean amount of money is 1, then there should be some limit process where you're just seeing a sort of stationary, locally finite support random measures on RD, and that evolves according to a certain equation. But again, actually proving that, again, it's something we've been too intimidated to try and do. Something funny happens is if we try look at these same long-distance meeting rates down on the sort of finite d-dimensional torus, of fixing the dimension and letting the size of the torus go to infinity. It's somehow obvious that you have what we loosely call a phase transition. We have sort of qualitatively different behavior in 2 cases. But in the case we were talking about before, where alpha is bigger than dimension d, you're mostly meeting nearby agents. In that setting, where alpha is bigger than d, we're mostly meeting distant agents. So in some sense, we're close to the Kingman uniform case. Because the qualitative behaviors are quite different, you sort of assume that the results are going to be different, but somewhat magically they're not. It turns out that the order of magnitude, sort of as a function of size m, the order of magnitude of this time until one person has all the money just scales as m to the alpha sort of throughout on both sides of the purported phase transition here, so up to constants. And this is the trick that somewhat magically comes out of our the sort of martingale improvement of the elementary bound here. So we had also an upper bound of 1 over the minimum of the news, and it's just the fact that in this particular case, so on both sides of the transition probabilities, on both sides of the critical value, when you look at this harmonic mean of the news, it's of the same order of magnitude as the smallest nu. So the sort of lower bound we've written there ends up as the same order as the sort of invisible upper bound I haven't written, and that's slightly magic and surprising when we figured that out. Okay. So last topic, and this is work of Dan, part of his thesis. Again, when we talked about a compulsive gambler process, I said everyone starts off with unit money. Of course, it works exactly the same way if we start off with sort of arbitrary amounts of money. Don't have to be the same, don't have to be integer valued. So we can think of the compulsive gambler process as starting with 1 unit of money divided arbitrarily amongst n agents. And now we want to sort of shift our state space. Instead of just thinking of n agents as vertices of a graph, we think they're at positions in a metric space. And if we're in a metric space, then the natural thing to do is to think of meeting rates as some function of distance, decreasing function of distance, say. And again, it's fairly natural to think of these meeting rates going down to 0 as d goes to infinity. It doesn't really matter here. For technical reasons, we want the meeting rate to go to infinity as d goes to 0, and this is because we just want to, we're going to do a framework that sort of doesn't allow 2 different people at the same position in the metric space, so sort of having infinite meeting rates kind of stops that happening. I mean, much of what we say would we presume go through in a sort of slightly different formal setup where we did allow 2 different people at the same point. but we just chose not to do that. But the point is that by disallowing that, one can think of the state space just as a finite, the state space just as a sort of arbitrary finite support probability measure on the metric space. And so we have the same process, or we'll give the process the same name. We can think of the compulsive gambler process, which evolves in the same way, but now as the state space as finite support measures. People are still meeting each other at these rates. So now the heuristic idea here is now think of a general, that we should think of as a continuous probability distribution mu on our metric space. Then we all know that we can represent that as a limit in the weak topology of uniform distributions on a finite set of points. Again, a typical IID realization would work, but we don't even need to do that. So somehow if I take a sequence of distinct points, Sn, such that the uniform distribution on S1 up to Sn is converging weakly to mu, then for each n, I can construct a compulsive gambler process in this finite set. It's just a finite state Markov chain, but now thought of as taking values in finite support measures, sort of random probability measure process. So for each n we have a process. The time zero distributions are converging to mu by definition, and it's sort of very plausible to think under suitable regularity conditions that the whole process will converge to a limit process. And that's the idea we're trying to formalize, that we can somehow make sense of this idea of this mechanism starting at time zero from a general probability, from a general or from a continuous probability distribution on our metric space. And the actual theorem comes out here. I mean, these exact regularity conditions we're maybe not sure about, but it's in a long paper on arXiv by Dan. So what we want to say is that, again, for each initial measure, we can define the process, and the idea is somehow the property of the process is that, if I look at the process started at some time t0 just bigger than 0, then it already has finite support, and therefore it just evolves in the sort of elementary way that the compulsive gambler process evolves, and we want that together with a kind of almost sure convergence. As t goes down to 0, these random measures converge almost surely, again, in weak topology, to the initial mu 0, and of course, just for niceness, we want the property to have the Feller process, that the distribution we see at time t as a continuous function of the initial distribution here. So we think this is true under various assumptions. So the current version, Dan will correct me if I'm wrong, is sort of the space is separable and locally compact. And I cheated slightly in what we said, that if the initial measure has compact support, then we get what I've said, which is sort of we get finite support for the process at times bigger than 0. In general, the best you can hope for is locally finite support, and again, we have results along those lines. So the proof, as you might imagine, is technical in detail, but it's sort of using, in part, some of the techniques we mentioned before. So we have our token process construction, and I don't know, repeating the story of, we can, instead of thinking of the compulsive gambler process as evolving in time, we can think of it evolving sort of banknote by banknote. And so the point is that by thinking of, by going back to my idea of thinking of the metric coalescent as a limit as n goes to infinity of the compulsive gambler process started with uniform money on S1 up to Sn, if we do that explicitly with IID samples, S1 up to Sn, of course we're introducing more randomness, which is making things a bit conceptually more confusing, more complicated. But the point is now we have sort of a coupling as n varies, because of course I can just sort of initially take an infinite IID sequence and then do the sort of nth construction from the first n. But we now have a sort of almost sure construction, a sort of coupling of these processes, mu n as n varies, and it's easy to guess, and actually true, that we now have an almost sure construction, so we can sort of define the metric coalescent as the almost sure limit of these constructions as n goes to infinity. And again, this involves exchangeability, but in a slightly subtle way. You know, most of the time, one uses sort of Diffinetti's theorem. The sort of objects are sort of automatically exchangeable. You somehow know they're exchangeable. You don't have to work to prove it. I mean, I guess the sort of occurrence of exchangeability in the Polyurban scheme is maybe one of the few subtle instances of exchangeable. Here, the kind of the property that sort of we obviously have is something a bit weaker than exchangeability, and it's so slightly subtle that this is actually equivalent to exchangeability. So I had this interchange with Dan, where sort of he gives me a 3-page proof of exchangeability, and I look at the first paragraph and say, this can't possibly be right. I'm not going to read it. So just because experience, you sort of know what works and what doesn't work from experience, and you're sort of too confident in your own intuition. So fortunately, Dan persisted and made me read it, and of course he was actually right here. So a subtle argument that somehow looks wrong but is right here. And the other thing is, so that's good advice on dealing with students here. The more subtle point was this sort of lengthy tree calculation whose details don't matter, but the bottom line is that the formula for a moment involving summing over k tuples, k is the moment we're trying to do, k tuples of agents chosen from our n agents of a complicated function p, and this sort of p is a complicated function with a number of terms, but the number of terms just depends on k, and that was the key point, not on n. So the sort of summing we're doing is summing over k tuples, and so ultimately we've got to do a sum over we've got to do an average over k tuples chosen out of n, to have an n to the k sum, but we're in a world where averages converge to integrals here, so at least an intuitive way, a kind of separate way of thinking about this metric coalescent, instead of the almost sure construction, is a sort of weak convergence idea that we can sort of compute these moments, and we can sort of say what the limits of all these moments are, just as the kind of same operations in the finite case, but with sums replaced by an integral with respect to the probability measure. So in principle, we could establish the existence of a limit process by a sort of method of moments, the Laplace functional method, just because we can write down what we want its moments or what we want its Laplace functional to be. Again, we didn't really pursue that idea, but it's a sort of separate argument for kind of the existence of this metric coalescent, again starting from an arbitrary measure. And the final thing, we sort of want to connect up the time t finite support distributions with our initial arbitrary distribution mu 0. And here we sort of do this by a martingale argument. Things are martingales in forwards time, but that can't somehow controls us. Upcrossing inequalities, etc., work in backwards time too, so we can get control over almost sure convergence in that way. So, with good timing, I have saved myself many more details on that. The stuff I've talked about is in a sequence of papers all on the archive, and thank you for your attention.
Anybody have any questions or comments? What about some social democracy here? What about redistributing the wealth? And
that's a good question. So we actually thought about that on the complete graph. So you're right. So if you kind of combine this with a percentage tax that gets you're taxed by 1%, and that's redistributed equally. So that then, of course, on the complete graph, you sort of expect there's some limit, and by golly, you can sort of find a partial differential equation for the Laplace transform of this. So there you are. So I know enough to write down a partial differential equation for a Laplace transform, and now I sort of want an old-fashioned applied mathematician to carry on with that. So at that point, yes, I have a list of somewhere a talk of probability problems that you get through a PDE, and then I stop and I'm trying to persuade PDE people to look at my PDE, because nobody actually wants to look at a specific PDE. The theoretician's existence and uniqueness, not actually solving it. So we sort of want to go back 100 years when people thought about actually solving particular PDEs. Yeah, yes. Okay.
You mentioned basically that the extension to the case of the finite dimensional lattice is kind of difficult, right?
Well, again, it's a quantitative question. You know, in dimension 3, there's sort of a number for the sort of limiting density of solvent agents, and actually, experience in estimating such numbers is typically very hard.
And so, but the case of the regular graph, it's kind of solved recursively, right?
On the tree, you can solve it recursively, yes.
So
Or again, solve in the sense that you can write down equations for the Laplace transform, which we can't actually solve explicitly, but we can bound explicitly. Yeah.
So perhaps it's like an intermediate case between the finite dimensional lattice and trees. It's a trees constructed from the hypercubes.
Okay.
Then you have like the same connectivity like d-dimensional lattice, and also the loop structure, the local one, is also there. So it's kind of like,
okay.
for example,
that's a thought, and we certainly didn't think of that one. Yes. So so I'm certainly encouraging anyone to work on any examples they can. Yes.
All right, well, if there are no further questions, let's thank David again.